In this physical world, engineers are often required to monitor or control the flow of various fluids, varying from thick oils to light gases through certain vessels. Considering this, Bernoulli's theorem provides a mathematical means in understanding the mechanics of fluid, ranging from aerodynamics to calculation of wind loads, designing water supply and sewer networks, and even measuring the flow using devices are some of its real-life applications. The flow measuring apparatus is used to familiarize students with the typical methods of flow measurement of an incompressible fluid, and at the same time, demonstrate the application of Bernoulli's equation. Although the expression for Bernoulli's theorem is simple, the principle strongly associated with the equation plays an essential role in the technological advancement designed to improve the quality of human life. Devices used in flow measurement and in investigating the validity of Bernoulli's equation, such as Orifice, Pitot tube, Venturi meter, and Weir, will be introduced in this experiment. The objectives for this report is first, to differentiate the different flow measuring device. Second is to determine the water's flow rate and coefficient of discharge using different flow measuring device. Third, to observe the changes in the characteristic of water in different flow measuring device through experimentation.
One example of flow measuring device is Orifice meter. Theory: Orifice meter is a flow meter which is used to measure the flow rate of liquid or gas using the principle of differential pressure measurement. It is also known as pipe orifice or orifice plate. It may be installed in pipeline. It also consists of a flat circular plate which has a sharp-edged circular hole called orifice plate. Orifices are usually in circular, rectangular, or square cross-section, but in this experiment, we'll be focusing on the orifices that are in a circular cross-section. The plate is held in the pipeline between two flanges. Orifice plates are used for a wide range of applications of fluid and operating conditions. For its advantages, it is economical and it doesn't need regular maintenance. Present on your screen are the photos of Orifice meter. The one encircled is the actual photo of Orifice meter installed in the flow meter demonstration unit. The one in white background shows the parts of the Orifice meter. It includes orifice plate, nut, stud, and flanges. It is also shown here the inlet flow, vena contracta, and the outlet flow. For the inlet section, it is a linear segment extending from the distance and acts as an end connection for the flow or for the fluid flowing inside. Outlet section, also a linear segment similar to inlet section where the pressure of the gas or fluid discharge is determined. Orifice plate. It is present between the outlet and inlet segment and used to generate the pressure drop which enables the measurement of the flow rate. Lastly, vena contracta. It is a point in a fluid stream where the diameter of the stream is at the least and the fluid velocity is at its maximum. It is a place where the cross-section area is minimum. For the apparatus, the only apparatus used was a flow meter demonstration unit. The parts of this unit will be further explained in the video that will be presented later. For the procedure, first step, open the delivery flow control valve. Step number 2, switch on the power supply to the pump. Step number 3, open the valve fitted to the orifice tapping. Step number 4, note down the manometer heads, which are the H1 and H2. Present on your screen is the YouTube manometer. The values above the zero mark are positive, and the values below the zero mark are negative. The difference between these two readings is called the differential head. And this differential head will be used in calculating the theoretical flow rate. For step number 5, note the time taken for collecting 10 cm rise of water in collecting tank. Step number 6, change the flow rate and then repeat the experiment. Last step is switch off the pump after completely opening the delivery valve.
So now we will be going with the Orifice meter instrument. Okay. So here it is the same as that of the Venturi meter instrument, what we have done. But the only change is that the different kind of instrument we are using, that is the Orifice meter, to calculate the flow rate of water which is flowing through the pipe. Okay. So this is a closed pipe. So for a closed pipe we are using Orifice meter to measure its flow rate. So we have seen Venturi meter, so now we are going with Orifice meter, and the procedure remains same. So the Orifice meter is made up of two pipes, and in between we are placing a Orifice plate through which the fluid is flowing. And that Orifice plate, Orifice is nothing but called as a kind of hole through which the water is flowing. Its diameter will be less. Okay. So whenever the fluid is flowing through this, there is an obstruction which is given to that, and that obstruction is getting very smaller. Okay. After that obstruction, after this part, the fluid will flow again with the same diameter, in the same diameter of the pipe. So Orifice meters are having less coefficient of discharge with respect to the Venturi meter. So we are getting the value of coefficient of the, generally the coefficient of discharge value for the Orifice meter is around 0.6 to 0.7 nearly. Okay. So in this range only we are getting the coefficient of discharge for Orifice meter. Okay. And the same amount of fluid is flowing through the pipe. So the procedure is same as that of this, as what we did in Venturi meter. So we will just make it again. We will just show it again to you. So what we are doing is we are starting the motor first. So we are before starting the motor, we are making sure that the one of the valve is open. So as I want for Orifice meter, I will open up the valve. Okay. I'll open up the valve over here. Okay. And after opening the valve, it is made sure that the water only flows through the Orifice meter pipe. Okay. So after opening the pipe, I'll start the pump. So the water will go on discharging and it is flowing through the Orifice meter pipe. That is, this Orifice meter pipe is letting the water to flow through. As I have said, this is the main tank, this is the measuring tank. Okay. Now the same procedure. So what we'll do? We'll open this. So the water, whatever is there, it will be dripping into this pipe and entering into this manometer. So here we can check the measuring H1 and H2. So to measure that H1 and H2, what we are going to do is we are going to close this. So we can achieve a pressure difference over here. So we can achieve a pressure difference over here. So we that is H1 and H2 difference, H1 and H2. So this H1 and H2 is known from the scale, that is this much, this centimeter, and in terms of centimeter we are getting this. After getting this, what we are going to do is we are going to measure the height of the water which is to be filled in this. That is for 10 centimeter, how much time it has taken to fill this water. So before going for this, we have to close this. Then we have to measure the water which is filling in this. For 10 centimeter of water rise, what is the time taken? So that is your time t. And after doing this, we are closing this. Okay. And we are shutting it down. So how to shut it down? So what we are doing is, before shutting it down, we are closing this. After closing this, we are gonna stop the pump. And at the end, we are gonna close the valve. So the same procedure is as that of the Venturi.
The formulas to be used in this experiment are the following. First one is the theoretical discharge. Theoretical discharge is equals to A sub 1 times A sub 2 times the square root of 2GH divided by the square root of A sub 1 squared minus A sub 2 squared. A sub 1 is the inlet area of orifice meter in meters squared. and it is in the formula pi over 4 times the diameter of inlet pipe squared. A sub 2 is the area of the throat or orifice in meters squared, and it's in the formula pi over 4 times the diameter of orifice squared. G is the acceleration due to gravity, which is in 9.81 meter per second squared. H is the loss of head. It is the density of mercury minus the density of water times differential head of mm of Hd divided by the density of water times 1000. The next formula is the actual rate of flow. The actual rate of flow is equals to A times R divided by 1000 times T, which is also in cubic meter per second. A is the area of the collecting tank. R is the rise of water level for the time T seconds in meters. T is the time taken for 10 cm rise of water in seconds. And lastly, for the coefficient of discharge, which is C sub D, it is equal to actual flow rate divided by the theoretical flow rate. This is the raw data table. Given here are the manometer reading, the rise in water level, and the time for 10 cm rise. Given also are the area of collecting tank, which is 0.12 square meter, area or acceleration due to gravity, which is 9.81 meter per second squared, diameter of the inlet pipe of the orifice meter, which is 25 millimeter, diameter of the orifice meter, which is in 12.5 millimeter, density of mercury, which is 13,600 kilogram per cubic meter, and lastly, the density of water, which is 1,000 kilogram per cubic meter.
Next is Venturi meter. A Venturi meter, or also known as differential pressure flow meter, is a meter device that is usually used to measure the flow of a fluid in the pipe. It can also be used at any specific point to increase the velocity of any form of fluid in a pipe. It functions practically on the principle of Bernoulli's theorem, where it states that a region of fast-flowing fluid exerts lower pressure on its surroundings than a region of slow-flowing fluid. The Venturi meter is invented by an American engineer, Clemens Herschel, and named by the Italian physicist Giovanni Venturi. By observing the effect of constricted channels on fluid flow, he designed an instrument with a narrow throat in the middle, fluid passing through the tube that speeds up as it enters the throat, where the pressure drops. And for the apparatus, we will need a Venturi meter apparatus, which is used to calculate the velocity of fluid in running through a pipeline, and a corresponding pressure drop from which the flow rate can be deduced. Then, the hydraulic bench. It will be used to provide the continuous and controlled supply of water in conducting the experiment for the Venturi meter. Now for the procedure. Before doing the first step, make sure that the air purge valve on the upper manifold is tightly closed. Then you can now set both apparatus flow control and bench supply valve to approximately 1/3 of their fully open positions. And then start recording time using a stopwatch at the moment we open the flow control valve. Water started to flow in the inner tank. When the meter indicates 5 liters water volume, stop the timer and turn off the flow control valve. Once you're done, you can now release the air purge valve to allow the rise up to the manometer tubes and form the hydraulic grade line, or HGL. We will be doing 5 runs by changing flow rate. Also measure the height in manometer tube A inlet and height of water in manometer tube A throat. When full flow is obtained at run 5, there will be a difference between the Venturi inlet A and throat B. Then you can now compute for your calculations. Now, the formulas we will be using for the measured discharge or flow rate. Measured flow rate is equal to V over time, where V is the volume of the tank in cubic meter and T is the time recorded for different flows in seconds. And for the calculated discharge is equal to V times A, where A is the cross-sectional area in squared meter and V is the velocity in meter per second. Velocity can be calculated using the continuity equation and Bernoulli's energy equation. And the last formula would be coefficient of discharge, that is equal to the measured discharge over the calculated discharge. The tables shown are the data gathered for the experiment.
The third flow measuring device is the Pitot tube. Pitot tube is a bent tube having both ends open and is used to measure the velocity of fluid flow or the velocity of air flow, as it is used in airplane speedometer. As you can see in the picture, the tube was named after a French physicist and engineer Henri Pitot in the 18th century, in which it is used to measure the speed of canals and rivers in France. Let us observe the GIF above. The tube works by first placing it in a moving stream of liquid with its open end oriented in the direction of flow. The liquid then enters through the opening until the surface in the tube rises h above the surface of the stream. After some time, an equilibrium condition is then established, where we can observe then the liquid in the tube remains unchanged as the flows remains constant and steady. For a better appreciation, imagine a particle at point 1 moving with a constant velocity v directed along the same direction pointing to the stagnation point. As the particle reaches point 2, its velocity is steadily retarded to 0 at the stagnation point. This equation now shows how the head at point 1 is transformed into pressure head at the stagnation point. Using Bernoulli's energy equation, we came up with a formula in it to calculate the velocity of fluid flow given the difference in height in the device. For the apparatus, this is what we use in laboratories. It is composed of 8 static holes and total pressure tapping, diameter 2.5 mm, a transparent tube, a 32 mm internal diameter, and a 430 mm length approximate, hose connections, and a water manometer for 180 mm length, and an easy and quick built-in coupling system. For the procedure, these are the steps in setting up the device. For a clearer understanding, please watch the video.
Bench, or that is called Pitot tube. Okay. First we saw the different types of parts we are using in this experiment. First one is this is the main supply, and this one is the motor. This motor will rotate this blower. This is called blower. Next is your valve. Next, this is your Pitot tube. This is the Pitot tube, and this one is your, you can say this is a manometer, through which we can take the manometer reading. Then we will start the machine and take the different readings from H1 and H2 value, and then we will calculate through this formula. Okay. Now I start the machine. Now we start the blower. Okay. Through this blower, through this valve, we can adjust the flow of air. Okay. How much amount of flow we need, we can adjust like this. Like this, we can adjust the flow of air. Through this flow of air, this is the Pitot tube, and this one is the nozzle. This is the outlet of the Pitot tube. You can see this is a nozzle. Okay. So how much amount of flow will takes place, we are finding out through a formula that is called discharge formula. Okay. Through this formula, we will study in your theory that Q is equal to area into velocity. What is the area of this Pitot tube and what is the velocity? To calculate the velocity, we need some pressure difference or height difference, you can say. So this is the difference. Inside this pipe, we are using basically water. When the air will flow to this one is the output through which the air will flow like this. Then this flow through this pressure of the air, this is the difference. This one is the H2 value and this one is the H1 value. Through this H1 and H2 value, we are getting the pressure difference. That is V. V is equal to root over of 2gh. We are calculating the V. Then we will take how much amount of rate of flow will take place. We are getting. Okay. Next we are calculating the. Directly go to the.
For the formula, we will be using the Bernoulli's energy equation, where V is the velocity of fluid flow, G is the acceleration due to gravity, and H is the difference in height. The formula is derived by observing 2 points, equating the changes that undergoes. For the final formula, V is equal to the square root of 2gh, where h is the difference. Lastly, here are the raw data tables for easier analysis.
Now, the next flow measuring device is Weir, and for this experiment, we will be introducing rectangular and triangular weirs. A weir is a barrier across the width of a river or stream that alters the characteristics of the flow and usually results in a change in the height of the water level. The relationship between the flow rate and water depth above the weir can be derived by applying the Bernoulli's equation and by making the same assumptions with regards to head loss and pressure distribution of the flow passing over the weir. Practical application of weir includes measuring or regulating flow in rivers, streams, or even irrigation canals. Since there is a unique relationship between the critical depth and discharge, a weir can be designed as a flow measuring device. It can also be constructed to raise the water level in a channel to divert the flow to irrigation systems that are located at higher elevations. It is same as an orifice without having an outer boundary. The difference between large orifice and weir is that the flow of liquid coming out of orifice is called jet, while on the latter it is referred to as nap, sheet, or vein, but most commonly nap. Now introducing the flow through a rectangular notch. Consider the flow in an element of height delta h at a depth h below the surface. Assuming that the flow is everywhere normal to the plane of the weir, and that the free surface remains horizontal up to the plane of the weir, then the velocity through element is equal to square root of 2 multiplied by g and h. The theoretical discharge through element will be then b multiplied by square root of 2gh multiplied by delta h. Now integrating this to obtain the total discharge between h is equal to 0 and h is equal to capital letter H, the total theoretical discharge will be as shown on your screen. In practice, the flow through the notch will not be parallel and therefore will not be normal to the plane of the weir. The free surface is not horizontal, and viscosity and surface tension will have an effect. There will be a considerable change in the shape of the nap as it passes through the notch with curvature of the streamlines in both vertical and horizontal planes as indicated in the figure. In particular, the width of the nap is reduced by the contractions at each end. The discharge from a rectangular notch will be considerably less, approximately 60% of the theoretical analysis due to these curvature effects. The coefficient of discharge, or C, is therefore introduced so that Q actual is equal to Q theoretical, and upon certain derivations, we will be coming up with this equation shown at the bottommost right part of your screen. And for the equations that we will be using through this experiment, the flow rate and the weir factor will be as follow. For the rectangular weir data, the table shown shall be used and filled out using the formulas introduced.
The name for a triangular weir is very descriptive. It is a sharp-crested tin plates with a V-shaped opening as presented in the picture. Triangular, or also called V-notch weir, measures low discharges more accurately than horizontal weirs. The V-notch is most commonly a 90-degree opening with the size of the notch inclined 45 degrees with a vertical. Since the V-notch weir has no crest length, much smaller flows are represented by the given head than for a rectangular weir. For a triangular weir, the actual flow rate can be expressed as QA is equal to 8/15 multiplied by C square root of 2G multiplied by tangent theta over 2 times H raised to 5 halves, where Q is the flow rate, C is the discharge coefficient, H is the height above the weir base, and theta is the angle of the triangular weir. Note that on the case of theta being equal to 90 degrees, the formula QA is equals to 1.4 multiplied by H raised to 5 halves can be used. The apparatus needed for this experiment are the following: hydraulic bench, vernier height gauge, stopwatch, and the rectangular and triangular weirs. The procedure for this experiment is first, start the pump and slowly open the bench regulating valve until the water level reaches the crest of the weir, and measure the water level to determine the datum level. Second is to adjust the bench regulating valve to give the first required head level of approximately 10 mm. Measure the flow rate using the volumetric tank or the rotameter. Observe the shape of the nap. Third is increase the flow by opening the bench regulating valve to set up heads above the datum level in steps of approximately 10 mm until the regulating valve is fully open. At each condition, measure the flow rate and observe the shape of the nap. Last is close the regulating valve. Stop the pump and then replace the weir with the next weir to be tested. And then repeat the test procedures. The collected data when the triangular weir is used in the experiment are the following.